In the previous video, we worked a little bit with proportions and how to solve proportions that had an unknown. And now we're going to talk about some examples of applying proportions to problems. So any application problem that can be solved using a proportion involves a ratio of two quantities. So a ratio is a comparison between two mathematical quantities, two numerical quantities. So you can recognize a ratio problem if you see things that are being hooked together. So if you talk about the examples we have here are, if we're talking about for a certain number of miles traveled, you use a certain number of gallons. So that's hooking those two quantities together. We might have a problem where we hook hours worked to wages earned. So that means there's a ratio of hours worked to wages earned. The more hours worked, the more wages earned. And then on a map scale, you might have an issue of distance on a map related to actual distance in the real world. So if you see things like that look like there's a couple of sets of numbers being hooked together, sometimes ratios and proportions can help you work those word problems. So the first thing we'll do is when we identify what two quantities are being compared, and then we try to make a ratio out of it. So for some of the examples we just used, we have number of miles traveled as a ratio of gallons of gas. Miles traveled per gallon of gas. Hours worked to wages earned. Map distance to actual distance. So these are ratios that we use. We figure out in a word problem that there's a connection between these two numbers, and then we make a ratio, and eventually we'll use a proportion to solve the problem. So if you have a problem like this where this technique will work, there'll be enough information in the problem to write two different ratios comparing the two quantities. So it's not just hours worked and wages earned, but it's saying if I worked a certain number of hours, I know how much wages I'm going to earn. And then what if I worked a different number of hours? What wages would I earn? And so so you're looking for not only that connection between the two numbers, but you're going to see two different ratios for that. So setting these ratios equal to each other gives us a proportion that we need to solve the problem. Because remember, when we have a ratio and we make it into a proportion, if one of the four numbers in the proportion is missing, then we'll be able to solve for that missing number. So here's a word problem example. It says CPR should be done on a cycle of 30 chest compressions per 2 rescue breaths. If a total of 2,940 chest compressions were done during a rescue, how many rescue breaths should have been administered? So we look through here, we're looking for different numbers that are being connected. And if you notice on this problem, we're talking about chest compressions. And then this is also a really helpful word when you're working ratio problems. If you see something per something, so in the last thing we talked about miles per gallon, that gives you a really good hint that you might be able to use ratios to solve the problem. Because that per relates the two numbers. It says we have 30 chest compressions per 2 rescue breaths. So for every 30 chest compressions, we have 2 rescue breaths. And then remember, we talked about that in order to use ratios to solve it, there have to be 2 sets of those connections. So here we say a total of 2,940 chest compressions, and we want to know how many rescue breaths. So our ratio is going to be chest compressions and rescue breaths. Now here we could write the ratio either way. Remember we talked about ratio, the order in ratio matters a lot. Here, it doesn't matter which way we put the ratio. It means that once we write one of the ratios down, we have to make sure we do the other one in the same order. So I'll show you what I mean by that. I could write 30 chest compressions over 2 rescue breaths, or I could write 2 rescue breaths over 30 chest compressions. So order matters, but at this point, it doesn't matter which one we do. What's going to matter is when we make it into a proportion that we make sure we're writing them in the same order. So write the first ratio any way you want, but make sure that the next one is written in the same way. So I'm going to leave this one up. So 30 chest compressions to 2 rescue breaths. I got that from the original problem statement. And then I'm going to set that equal to, and I have my 2,940 chest compressions. And I'm asking how many rescue breaths. So I'm going to use X to stand in for that. So I don't know how many rescue breaths go with 2,940 chest compressions. So the reason we write it as a proportion is so that we can solve for the missing number. So I'm going to write it as an equation. I'm going to do this one. I'm going to do 30 chest compressions down. Remember, we're doing cross multiplying. So that's 30 times X equals, and then I'm going to take this one, 2 times 2,940. So I'm just making an equation here to solve for X, which is the number of rescue breaths which we want. So continuing to work on that equation, I get 30X equals 5,880. Just did that on my calculator. Now I'm going to divide both sides by 30. And I get X equals, again, doing this on my calculator, 196. Now I have to think about what is X. X is rescue breaths. So I'm going to say it's 196 rescue breaths. So if we go up to the top, think about what we were being asked. If a total of 2,940 chest compressions were done during rescue, how many rescue breaths should have been administered? Our answer is 196 rescue breaths should have been administered. So we found 2 quantities that were being related to each other. We wrote a ratio. Then we found a second set of those numbers being related to each other. Wrote the other ratio in the same order as we wrote the first ratio. Set them equal, that makes them a proportion. And then we use cross multiplication to make an equation that we could solve. So now we're going to talk about using proportions to solve similar triangle problems. So remember we said before that if 2 triangles are similar, they have corresponding sides. And so those corresponding sides are proportional. And that means they have the same ratio. And that's what we're going to use in this next problem. So similar triangles and proportions can be used to solve for the length of the side of a triangle in a similar triangle problem. So if I tell you that these 2 triangles are similar, and just to simplify things, I'm I've lined them up so that corresponding sides are lined up. Remember we talked in an earlier video about sometimes it's hard to figure out which side is corresponding to which, but to simplify this one, I've set them up so that the corresponding sides are lined up so you can just look at them and figure out which sides are corresponding. That's not always the way it works, so you do have to make sure you know which side corresponds with which. You can't just pick any side on one triangle and say it corresponds to just any side in the other triangle. So because we know these two triangles are similar, we know that the ratios of their sides are equal and make a proportion. That's a new thing. That's what we're going to use to solve these problems. So I want to explain to you what that means. So that means that if I pick one side of LMN, triangle LMN, and then I set it up as a ratio, remember that just means set up this ratio with the corresponding side in the other triangle, then that's equal to another side of LMN in a ratio with the corresponding side of that other side in WXY. And we're going to work one with all the numbers to see how that works. Okay, so that means, for example, if I pick LN in the triangle LMN, that means I'm picking this one, and I'm saying that corresponds to WY. So these two are corresponding sides. Remember I said I know that in this case just because I'm telling you that I lined these up so those are corresponding. In another video we talked about how to figure out what the corresponding sides are. So then, if those two are in a ratio together, then it means I can take any two other sides and put them in a ratio. And so that means I could pick LM over here, so that's this side here, and that'll correspond to WX over here. So we're setting up a ratio, corresponding sides on the two triangles equal to two other corresponding sides. And remember, the order matters a lot. So when I chose over here to put LMN on top, that means over here I have to do the same thing. So it didn't matter which order I put it in over here, but once I chose to put LMN on top, it's got to go on top over here, because the ratios have to be in the same order to set them in a proportion. So what we just said on the previous slide was that this was true. So now we can start plugging in some numbers. So LN is 10, and so this became that. And then WY was 4, so that went down here. Then LM is 12, so that goes here. And WX is the thing we're wondering about. And so we're going to let X equal the length of side WX. We could have left WX in there. We want to use variables so that we can put it in equation form. Okay, so we just lined everything up, and lining everything up properly in that ratio is what's important about this. Once you line everything up, it's fairly easy to solve it, because now we've just got the proportion like we had in the earlier video, because we've done all the hard parts of putting everything in the right place. So now we just have 10 over 4 equals 12 over x. We do our cross multiplying, so we have this one and this one. So we have 10x equals 4 times 12. So 10x is 48. Divide this by 10, divide that by 10. And so x is equal to 48 over 10. We can reduce this. So 2 goes into both of those, so we can get 24 fifths. Depending on the problem we're working with, we've talked about this in class, that you have to kind of use some judgment about when to use decimals, when to use fractions. We can leave it like that, or we could make it into a decimal, which would be 4.75. No, not 4.75, 4.8. So use your judgment whether to leave it in fraction or make it a decimal. What we've talked a lot about in class is you typically don't want to make it into a decimal if that's going to wind up rounding it, if it's not an exact decimal. Okay, so this is the slightly harder version of that problem. It's the same thing, except that now you actually do have to figure out which one corresponds, which side corresponds with which. And this is the one where they're rotated and flipped, and so you can't just look at it and say, and connect the two sides like I did on the previous one. So this one is saying you're going to have to figure out which sides correspond. And so there's a little trick to this. So listen carefully about this, because it's a little bit subtle, I think, but it's a really good trick. So the order that these letters in the name of the triangle, the order of those letters matters. And so if you look at the red one, when I have QRS corresponding to UVW, that means that Q corresponds to U. So I'm going to use the red that I have there. So Q goes with U. And then if you look at my blue, S goes with W. Now, if you're like me, that starts scrambling your mind, because again, I'm a visual person, so I need to see those two lined up correctly. So you could do a little sketch if you wanted to, and just take this triangle over here and flip it around so that W was in the right place to look like it corresponds with S. But for right now, the reason I use those two is that it says find the length of side WU, and so I know I need to, so QS and WU go together. So this one, this side is going to go with this side. Now I'm not saying that this one is 12, I'm saying these two go together. And then I have to pick two other ones. So if all of that is true, then we also know, because we already said Q goes with U, S goes with W, that means R goes with V. And then that means I also know that this 8 goes with that 3.2. And that's the crucial thing, because remember, when we set up our proportion, we won't be able to get anywhere unless we have two sides that we know correspond with each other, and that we know both of the lengths. So this one goes with this one, so that's our first ratio, and then this one goes with this one, makes our second ratio, and that's how we're going to end up solving for it. So we're going to write that out as a proportion. Put that up where we can see it. So remember, the order doesn't matter, but once I pick it, I have to stick with it. So I'm going to do my 8 goes with 3.2. Now I've picked my order, so that means it has to be 12 goes with, I'm going to call this X again. So once I've picked the order, they have to stay the same. The 8 came from this triangle over here, and so the number on top on the other proportion, the 12, also has to come from this triangle over here. So now that we have the proportion, that was the hard part. So be really careful setting up that proportion. The hard part is deciding what sides correspond. Solving the proportion is not the hard part. So you all know how to do that. You're going to do your 2 cross multiplications. So I'm going to do 8x equals 12 times 3.2. Divide, whoops, before I divide, I better multiply over here. So 12 times 3.2, if I do it on my calculator, gives me 38.4. So I have 8x equals 38.4. Now I'm going to divide both sides by 8. And then again on my calculator, 38.4 divided by 8 is going to give me 4.8. So x is equal to 4.8. That means that this side here is equal to 4.8. So these can be a little bit complicated and confusing. We'll work on them in class. So try to understand this. Look at a couple of worked examples in your book. And then when we are in class working homework, you can ask questions about this and work together on it.